So this is Hassan from Magicplan. I'm a member of the research team working for Magicplan. So let's start with what Magicplan is. Magicplan offers a better way to get work done while in the field. It offers a mobile solution to create and share sketches, field reports, and estimates. It helps people connect with their team members and understands what's happening on the site without even having to go there. And it will use many features that are powered by AR and AI technology. Our target customers are mostly restorations, renovations, inspections and claims, building and facility management. As I mentioned, I am a member of the research team, and the focus of our research team is mainly around capturing the indoor scene and bring it into the 3D estimation of the layout of the room. So there are many models working under the hood. We are predicting corner, edges, we have object detection, plane detection, depth estimation, and many other things are working under the hood. This is our main focus. But today I'm not going to talk about these features. I'm talking about other project that we are working, because research team is also involved in any other AI related task. And one of those tasks is an interesting feature that we are about to add to the next version of Magicplan, which is the auto-furnishing feature. So here I'm just going to talk about the story that we had when building this feature, how we defined the problem, what was our solution to those problems, and overall what was our journey to bring this feature into the final production. It includes, for sure, many AI techniques, mostly derived from academic studies, but in many cases, they're simple. There are some common things that you can see in academia. The aim here was not at the beginning to make any state-of-art model, it's just to bring this feature into the production for the business purposes. So let's start. What is auto-furnishing project? So we have manual furnishing already in Magicplan. So a furnished room better illustrates the floor plan, better shows the scales. It's an artwork for realtors, but it's a time-consuming process. For example, the user has to go through a library of objects, brings the one that he is interested in, put it in the scene, put it in the right scale, position, and orientation, and repeat this for every object and for every room in the floor plan. This is a time-consuming process, and we want to tackle this part to make it automated. So, sorry, it is not good. Okay. So before we jump into any solution, we first need to get to know what is our question, so to have a better proof of concept. So what is a good auto-furnishing feature? What is the quality of it? First of all, it needs to bring relevant objects to the scene. It needs to respect logics. It has to be realistic. Objects should not collide. There should be no door block, no block path. Objects should be in relations. They should have realistic size. The room shouldn't be underpopulated. And it should have some symmetry. Other things that are Magicplan specific is it doesn't need to be detailed. We don't aiming to have very dense scene, because the final result is a 2D top view of the room. So even a very crowded scene might be even a negative. Other features we need to have is the model has to be diversified. We need to have an input, a simple room, and have multiple options for how we can furnish this room. And we also have some technical limitation for any model that we want to bring into a mobile app. We need to take care of the execution time, the model size, the kernel size, how much memory it takes, and the limitation that we always have. So, first of all, we thought that question might be very simple. This question to furnish a room might not be a 3D problem, might not be a 2D problem even. It might be even a 1D problem. So if you look around, if for sure some of you might be in your home office because of the pandemic, if you look around, you see the furnitures around are mostly wall-based. And even non-wall-based objects are mostly attached to a wall-based object. For example, a chair, which might be in the center of the room, is attached to desk most of the time, which is attached to a wall. And walls as edges of a closed polygon in a room can be defined in 1D. So how we can formulate a room in a 1D manner. It's easy. Flattening the room in a 1D line, putting object across this line, and reshaping the line back to its original polygon. Let's explain on this figure. For example, assume I start from here. I have multiple 1D signals that I'm gonna populate. I move from here, I have balls. I'm starting from here, I have balls, and then I see a bed. Then I see a corner. The corner is here. This is a signal for the corner. Another wall, there is a window, and so on and so forth. So I have wall, corner, door, window. Orientation is a sine and cosine of the orientation of the wall that we are talking about. And we have all the objects. So here, for sake of presentation, I'm putting only 2 object categories, bed and drawer, but we can have many multiple ones. Actually, in the final implementation, we have 26 objects. So this part, the top part, can define this room, uniquely define this room. So we brought this room to this complex shape into a 1D signal. And if our model can take this as input and can generate an output based on the criteria that I explained in the previous slides, we have the model because we can bring it back to this original shape. So how we use this? As you know from the title of this experiment, we're going to use GAN. So you are most probably familiar with this architecture. This is a conditional GAN. I just quickly go through it. So the way that we train this, we have our bedroom. We bring it to a 1D signal. This is a 1D feature map with 6 different channels. This is going to be our condition. This condition, along with the sample from normal distribution, goes to a generator, and the generator outputs the some furnitures. Then we concatenate the output with the condition and send it to the discriminator. A simple sample from a real distribution also gets chosen. Both of them go to the discriminator, and we have the GAN loss. Here, the unit is not the traditional unit, is a kind of a 1D unit because the signal input is 1D. The difference is that the kernels are 1/3 rather than being 3/3. So after the training with our data sets, we can look at some of the results that we generate. So these are the results after post-processing. Just before I play this, I just want to tell that this is just for sake of visualization. We use other, actually, I don't know if you can see the reference here. We are using other objects which are not in MagicPlan UI to render the output of our model. So on the left, you will see that if you use the same room and navigate through the latent space, going from one point to the other, we can see that we have realistic room layouts that respect the room geometry and generating realistic furniture layouts. On the right, we have same latent vector, but different room shape. As you can see, the way that it gets furnished are pretty similar between rooms, but the model respects the room geometry and try to fit in the furnitures as they're not crossing, they're not colliding, they're not blocking the path, and it learned the general distribution of the scenes that we have provided in our training sets. So we were happy at this level, but immediately after this part, we found that this approach has multiple limitations. The biggest limitations are living rooms and dining rooms. Living rooms and dining rooms have many other dominant objects which are not wall-based. For example, the dining table. For example, the big coffee table in the center that defines the room. Everything is surrounding that table. These are very difficult to be defined in 1D. And also we have other limitation as well. When the rooms are small, when you use 1D approach, the objects from across the opposing walls collide to each other because the 1D signal that we presented to the model is kind of limited in providing such information. And in the small rooms, we also have blocking patterns. So we said, okay, 1D might not be it cannot be generalized to every approach. What we can do? So why not use it 3D? We have the model that can be learned in 1D. Why not just bring the condition as a 2D signal and ask a 2D output of the layout? So how we can formulate it? It's even easier than 1D. We have a room. Our condition would be an empty room, and the network output should be the objects. So here, each object is color-coded. We have multiple object categories. We have one color for each object category that we have in our database. As you can see here we have a background, red background in the condition. This red just say that this room is a bedroom, because our model finally gonna populate every other room types. So we have different color. It means that different room different type of room needs to be populated. So different objects can be placed. For example, same shape geometry might be a kitchen. So the model needs to know that we cannot put a bed in it. It has to be some cabinet, sink, and so forth. So going through that, we first try to use the conditional GAN, the way that we had in our 1D model, and try to learn with that model. It didn't work. When we moved from 1D to 2D, many things changed. The network was not as stable before. Finally, when we tried to make it in a stable training, we had mode collapse, we have almost no diversity, and final results was not satisfactory at all. After many iterations, finally we end up with BicycleGan. This architecture, again, you probably are familiar with, but I quickly go through it again. It has two major blocks during the training. We have an encoder and we have a generator. The left part is just a conditional VAE. Actually, in the original paper, it has a discriminator as well. It has a GAN in it, but in our project, we did not have a discriminator here. It's a simple VAE. You send a furnished room inside the encoder. It encodes to this distribution. Then we provide the empty room. With this, we sample from this distribution, we send to generated, and we expect to reconstruct what we sent inside. And for sure, this we have a KL divergence loss here between this distribution and normal distribution, and there is an L1 loss between first and second. So same networks, same encoder and generator being used in a different setup. Here, we send a room inside an empty room, plus a sample from a normal distribution, and the output should be the room with some random furniture layouts. We use that and a sample from real data sets to a discriminator, and we have GAN loss. Aside from that, we use exactly the same encoder, exactly the same kernel here. This kernel has to predict what was the Z, what was the latent that we provided at the beginning when I wanted to sample it. And there is a long loss between this Z and the sample that we chose. So how we training, we do one iteration at this, one on that. So one forward and backward, one forward and backward. So these networks, these kernels get trained between these two architectures. During the inference, we're going to strip away everything that we have here. We have only this part. We send an empty room, we send a sample, and the generator should potentially output a furnished room for us. So let's go and see how it looks like. So before I play this, I just wanted to say these are different room types. The background color of the empty rooms tells us what room type it is. Blue is kitchen, these are bathrooms, bedrooms, and these are living rooms. You see many different colors here. Actually, there are 26 different colors. I believe on this to these 26 different colors. So I don't bother about what color is what. Just look at the general layout of how it's generated. So in each case, I'm just navigating into the latent space, just without any post-processing, without any investigation into the latent space. Just to send a random number with a condition, and this is what the GAN is out. So here we can't use this. This is an RGB image. When we want to populate a room, a real room in MagicPlan app, we need a list of objects with their bounding box and orientation. This is this cannot be used. I know this is a bed, these are some covers, but I have to instantiate the object from it. And meanwhile, the bounding box by itself is not enough. I need to know the orientation. I need to know this bed is facing this way, facing down, and these are facing to the right. So there is another step we need to take. And this, we go to the next slide. So in order to extract this object, we use object detector. And one of the interesting papers that we found in academia was object as point. This is a very simplified object detector, very fast and light. And I'm just going to explain a bit of what's inside it. There is a feature extractor with multiple decoder tails. Each of these tails responsible to predict some specific features of the input. And the most important one is the center point. So this center point map just try to predict where are the center of the objects. So after we found the center of the object, we find the position of the center where is an X and Y, and we read the values of other feature maps at that point. So if we have an object, we find its center, we can read what is the offset, how small we need to move it, what is the width and height of the bounding box, and what is its orientation. So this way, we can even find this orientation based on the general statistics of the rooms that we have in our data sets. We don't need to do any coding or any scripting logic for it. It's going to be learned this. So let's look at the final results. Okay, here are the output of our GAN models. These are RGB image. When we pass it through our center net, we get list of objects. And I'm here drawing this image based on a list of objects and the room shape. These are oriented bounding box, and I just show you for purpose of the presentation, the orientation that the model predicts. Same as here, this is the object, and this is the RGB image, and these are the oriented bounding box with their categories. And finally, when we have a list of objects, we can pass it to the MagicPlan app, and over that, with the API that we have, we can use the MagicPlan UI to present it in 2D. And finally, these are 3D objects. You can even show them in 3D. Final slide, how we're planning to implement them. This is not finally embedded in MagicPlan. It's going to come under the next version. But just some details of the way we have our training, and we have our training and evaluation. The model is developed in PyTorch. And it's difficult to bring it into the mobile devices because we need to convert many of the pre and post processing into other languages. We have Apple devices, we have Android. Some of this stuff can be done on a web browser. So there are so many rewriting stuff involved. And even the kernels has to be transferred. We have to bring it to the TF Lite or Core ML, and that part has some tricky stuff as well. So with this way, it is very difficult to modify the code later on, or even upgrade it, or do any troubleshooting, because everything has to be rewritten all the time. So we finally decided to put it on a cloud, and finally we decided to use Amazon SageMaker. Amazon SageMaker comes with a good PyTorch SDK. You just need to bring the code, your pre-processing, your kernels, and your post-processing in shape. The way now it works that the mobile device just send the vectorized empty room shape to our SageMaker. Here we render it to 2D for the condition of the GAN. Then we sample it from our GAN model. We send it to the center net. We get the list of the objects and pass it to the mobile device. And here on the UI, you can render it. The user can render it. Actually, the application can render it on the room. So I think this would be the end of my presentation. I just want to thank you guys, and feel free to use MagicPlan and test. And if you want to see other features that we have on the room, specifically on the room captures that I've been explaining. Thank you.
Thank you so much, Hassan. That was super insightful and a really, really technical talk. Yeah, round of applause for digital claps for Hassan there. Jumping into some of the questions there, we have a question again from Wilco. Can I use MagicPlan to optimize the location of sensors, e.g. fire and smoke detectors across a building? for example, with the least number of sensors across the building, covering the maximum range of detection?
Okay, I might not be the best person to answer this question, but MagicPlan, for sure, you can design the entire things. You can design what you're asking here. You know how to put your sensor, but those type of calculation, I'm not sure if it's on MagicPlan yet. But again, I'm not the best person to answer this question.
Well, thanks for giving that a shot there. And we have another question here from Sarah. How accurate are measurements taken throughout MagicPlan?
It depends on the device. We're talking about less than 5%, but it depends on the user. There are some stuff that is not AI related. Depends on actually I'm focusing on that. Depends on the device, but less than 5%. We're talking about less than 10 centimeter, 20 centimeter when you're measuring the length of the ball.
Fantastic. Thank you so much for your question, Sarah, and for your answer there, Hassan. That is it for, do we have any other questions? We'll leave it a couple more seconds if anybody wants to pop one in. Here we go. We'll go again. How are you planning to resolve any connection issues when MagicPlan is going to use the cloud?
The point is, yes, actually, this was one of the things that at the beginning we were reluctant to go to the cloud at the beginning, because first of all, the users are mostly not in their own home. They're somewhere around that they don't even have internet connection to send the signal. But something that we have in this specific feature is that this is a post-capture procedure. This is not something that has to be done at the beginning, and most of the users even do it not on their own devices. They do it, this feature, the furnishing, on the web browser. But the quick question is, hadn't been deployed yet, we are not we're not sure about the problems that we are facing later on. This is already not even on the beta. This is just being tested by MagicPlan employees.